Now we're going to extend our line integral to 3D space. So we're trying to integrate this where C is defined as this line here moving through 3D space. So C is moving around this thing here in 3D space. So this is your X location. So the particle is moving along like this. You always know the X location, the Y location and the Z location of the particle as it moves through that line. So we are moving from t equals 0 to pi. So as it's moving along, we always know the X, Y and Z location. So we can put this, the X location, we can put the Y location and we can put the Z location into this function here. So you can think of this function as being this. So this whole thing here will spit out some sort of f value. So let's imagine it spits out. So when the particle is here, you put x into here, y into here, and z into here, and this whole thing here will spit out some sort of value f. So let's say it spits out the number 4. So what that means is when the particle is here, this whole thing here will spit out, let's just imagine, as a number 4. So you put the number 4 into your cup, and then let's say the particle is moving along. The particle is currently here at the moment. If the particle is currently here, then you always know the X location, the Y location and the Z location. So you put it into here, put it into the Y, put it into the Z. This whole thing here will spit out some sort of value. Let's say it spits out the number 5. So so at this location here, it spits, this whole thing here spits out the number 5. So you put the 5 into the cup, and let's say the particle is moving around here. Let's say currently the particle is here. So you put it into here, you put it into here, you put it into here, and then this whole thing here spits out, let's just imagine it spits out the number 1. So now you put the number 1 into your cup, and then throughout your whole journey you would sum up everything in this cup. So that's the idea behind the line integral as it's moving through 3D space. So let's try and compute this now. So the line integral, now extending it into 3D space, we now have 3 variables. So in 3 variables, remember, this is your X location, this is your Y location. You always know the X location, Y location and the Z location. And then to compute it, we need to know the speed, meaning this is our position vector. If we differentiate it, if we differentiate it, it will give us our velocity vector. But then this formula here will require the speed. So we need to take the magnitude of the velocity vector. So the magnitude would be this squared, using Pythagoras in 3D, this squared plus this squared plus this squared. And combining these two would give us the number 1. So 1 plus 1 would be 2, and then square root the whole thing. So we know the speed is root 2. So we know the speed is root 2, and we always know the X location. So when you put the X location into here, and we always know the Y location, so this bit here would be cos t times sine t. So that would then give us this thing here, cos t times sine t. And then we always know the Z location. Well, let's put the Z location into here. So this bit here will become t to the power of 3. So t to the power of 3. And then our time is moving from 0 to pi. So our time is moving from 0 to pi. From 0 to pi. So our line integral would become this. And we're working all in terms of time. As time ticks away, the particle will move along this line. So our integral becomes this. Hang on. Our line integral becomes this. So this is just a constant, so we can drag it out. That would then be this, and then when you integrate this is easy to integrate. It's just a half sine squared t. and then integrate this, it would then become this, and then from 0 to pi, from 0 to pi. So now put this into here. Sine of pi is 0, so the whole thing here would be 0. Put this into here, so that would be pi to the power of 4 over 4. And then when you put 0 into here, it would be 0. Put 0 into here, it would be 0. So our final answer is given by this. Okay.